Let me share my screen. All right. Thank you, everybody, for joining today. So this is the first community event for the RISC-V New York City group, in hopes that there will be many more to come, not just virtual, but also in person. And so this first presentation is really just an introduction about RISC-V, just what it is overall, some history, and how really anybody can get involved. And particularly in this session, we're just going to focus on the New York City group. But if you're anywhere else where that doesn't have a community group, there are ways that you can start your own community group. And we can talk about that in more detail during the Q&A session. So without further ado, let's get started. So for this session, this is just a rundown of the agenda. We're going to go over some background and some motivation about what RISC-V is, or why it's important. And then we'll go into a brief overview about RISC-V, about some of the history. Then finally, we'll go into how you can get involved in RISC-V, and what we're looking to do specifically in the New York City group. So from my perspective, just arranging some of the events that are potentially that we can hold in the New York City area, hopefully in person, as well as if we still want to do virtual or some sort of hybrid scheme, then that would be great. And then we can kind of, in this particular section of slides, we'll go into more detail about how what I think that would look like and how anybody really can get involved. And then finally, we'll just wrap up with the Q&A session. So just a little overview about the just the platform itself. Like, you can ask a question in the Q&A tab on the right, and then that'll just be visible to myself and the other presenters and Megan, who's the host, and then we can answer. We'll answer you directly. So I believe the recording will be available for later review, and I think we'll share details about how you can access that at a later time. So continue on with the next slide. So just a little bit about me. I'm Mohammed Belou. I'm the founder of Mab Labs Embedded Solutions. It's the website, that's the LinkedIn page. And I'm just an embedded Linux consultant where I help companies do board bring up, do custom driver development with FPGAs, custom peripherals, hardware that they want for their product, that they've developed for their product. I recommend everybody to sign up for our newsletter. You can scan this QR code, and then you can take benefit from some of the things that we learned, the projects that we're working on, some tips and tricks that we learned in embedded Linux, as well as the Octo project and RISC-V as well. So to get started, we can kind of just go back to basics, right? And some of the slides in this session will be really fundamental, just under the assumption that somebody's coming to this particular session without any real sort of background beyond just basic computer science and just general hardware engineering. They just want to get an understanding and a sense of what RISC-V is, why is it special? Like, it's starting to explode pretty exponentially in the past few years, and just to get a bit baseline about what the motivation behind that explosion is. So we kind of go back to basics, right? Like, if you have a processor, right, all it does is really take ones and zeros, right, which in itself are abstract manifestations of like 5 volts or 0 volts, and then just converts that into some sort of physical action. So it doesn't need to be a microprocessor. It can be a microcontroller that, based on certain actions or certain commands via these ones and zeros, actuates some physical device, resulting in some sort of operation, right? Or takes inputs, or accepts some physical other sensing environment, senses something in the environment and converts that into ones and zeros. So that's kind of really the basic element of what a processor or microcontroller does. It just takes bits, right, ones and zeros, and just turns that into some sort of physical action that can be observed in the real world, right? So the problem is that as humans, it's very difficult for us to make sense out of ones and zeros, right? Very few people can just look at a stream of ones and zeros and in their head understand exactly what is going to happen based on a particular specification of, let's say, a microprocessor. And if they can, given that specification, take those ones and zeros and determine or specify what the action that a particular microprocessor or microcontroller will take place, right? So it's not sustainable for human beings to take ones and zeros and convert that into a set of steps that a processor or microcontroller will take to perform a physical action. Instead, we need a mechanism to be able to convert, let's say, something that we want to do at an application and convert that into ones and zeros for a particular microprocessor, right? So we need some sort of middle ground. And so that's where this concept of an instruction set architecture comes in, or usually abbreviated by ISA. So what that does is it basically gives some structure to these ones and zeros so that, again, it makes our lives as human beings somewhat less difficult, so that it's easier for us to then figure out, okay, this is what I need to do, and in some pseudo language be able to convert that. And by language, I mean like the traditional, like English, for example, is a language, to convert that into ones and zeros that will ultimately instruct a processor on what to do, right? So that's where ultimately, like in very brief terms, where how the genesis of the ISA, or like what the motivation behind an ISA is, right? So this is a really kind of rough, and here we can see, like, this is an example of a MIPS 32, the breakdown of an add instruction for, let's say, a MIPS 32 architecture. Okay. And this is really just an image, again, just to demonstrate like how the ISA fits into the overall system that exists of an electronic system, right? So you have hardware and you have software, right? Software is a close representation of something that can be described by a human being as to what they want the ultimate goal for the processor to do. And the hardware is the actual manifestation of those actions. And then the ISA really acts as the intermediary between what the person wants to do versus what the hardware actually does. Okay. So there are a couple of kind of high-level descriptions or requirements of an ISA, right? It's really a contract or a specification between software and hardware. It doesn't define an implementation. So all it really does is says, here's all the things that the hardware can do, and here's how you can invoke these operations and access these hardware elements. And this is a contract. This is, if you imagine an API that the software needs to invoke to be able to perform a particular application or particular operation. And because the implementation is not defined in the ISA, the complexity is opaque, right? So me personally, like, I'm a software developer. I really don't care how the underlying processor goes about implementing what I wanted to implement. All I need to know is if I say I want to add 2 numbers, it ultimately turns into instructions, right, which ultimately turn into ones and zeros that instruct the CPU to add 2 numbers, for example. How that's done, is dependent really on the tool chain itself, right? So the tool chain, the compiler, ultimately takes my operations in a high-level language like C and converts that ultimately into ones and zeros. Compiler plus linker, like the entire tool chain, converts that into ones and zeros that a processor can actually make sense of. Okay, just one second. Sorry, just responding. Sorry about that. So, but the implementation and the definition of an ISA is not trivial. It's actually very difficult. And you need to make many considerations when you go about designing and implementing an ISA, right? So how many operations do you want to support? What types of storage mechanisms should be supported, right? How many bits should an instruction be, right? And how can you make it future-proof, right? As technology evolves, as processors become more available, become more powerful, right? You need to be able to support instructions that allow you to take advantage of the increased hardware complexity in the underlying processor itself and make that available to the software at a higher level. Okay, so now that we understand what the motivation is for an ISA, the question is, well, what's RISC-V, right? So if we take a step back, right, back in the 70s and 80s, there were a few dominant players when it came about to the ISA, right? So it was really the 8086 ushered in the era of really the microcomputer, and due to that, the x86 instruction set became the dominant force at the time. In modern days, ARM has become dominant as well, just because of their power consumption when compared to the x86 processors. And so they've been more predominant in the mobile space. And we're seeing actually more ARM processors being introduced also to the desktop and server space as well. So traditionally, the x86 and ARM ISAs have been the most popular. But the problem is these are commercial ISAs, so they come with certain restrictions, specifically licensing restrictions. So because so the ISA itself is a specification that is available, that you can actually read as a document, as a specification, but the actual implementation details, like how things are actually implemented, those are proprietary IP of the developers of these instructions themselves, of the instruction sets themselves. So they're generally patented, they're not necessarily visible. And so what that ends up happening is that it becomes really costly or restrictive for basically new players to join in to build hardware. So if, let's say, a hobbyist or an academic institution wishes to make, let's say, improvements to an ISA or add additional features or basically make some sort of an enhancement to the ISA, because of these commercial restrictions, it becomes very difficult for somebody like a small player to enter the market. So usually when you're talking to, for example, ARM, there's usually years of negotiation that takes place, substantial amount of money that needs to be devoted to this to the actual agreement to just procure, let's say, a design. And you can't even just customize it, right? All you can do is just use your existing design in your final hardware. So there is no real opportunity for somebody that's relatively small, that can't afford this time or cost, to be able to tinker with it, to be able to introduce their own innovation to it. So it's pretty restrictive. So like I said, because of these licensing restrictions, it hinders any meaningful product growth, right? Academia, small businesses, hobbyists, whenever they're dealing with these commercial proprietary ISAs, they immediately get ruled out, right? So in David Patterson and Christy and Anistovich's paper, we're going to see later on, he makes a pretty profound statement in saying that the problem with commercial ISA is that if a company dies, it takes its ISA with it. It's really important for the community, for the progression of the community as a whole, that to make this ISA available so that it's not just within the hands of a single entity or company. Everybody can take part in it, everybody has visibility to it, and everybody can expand upon a particular ISA and make their own relative improvements. So in contrast to a commercial ISA, we have the open ISA, right? And it's provided under open source licenses. So RISC-V is an open ISA. There is no fee to use, and it allows users to refine and contribute back to the community. So if you imagine, it's similar to how the Linux kernel works, right? You're free to download the source code. There's no fee to use the source code for the operating system or the kernel itself. and it lets you make your own improvements and customizations and contribute it back to the community. So RISC-V operates in a similar fashion, right? And so the great thing about that is it enables innovation because anybody has access to it, everybody has access to it. And so it enables opportunities for developers, again, small businesses, academia, hobbyists, tinkerers, to add their own extensions for their own improvements. If let's say they're developing some feature that has some hardware acceleration under the hood, then they can add their own instructions or have extensions to the ISA to take advantage of these accelerated features. So just some history, just to get some appreciation for where we are today, right? So Kristi Asanovich had, when back in the day when he was a researcher at university, he had a research requirement for an open source computing platform. So this was back in 2010. And so with the help of some graduate students, he developed and published this open source computing platform in 2010, right? And his motivation was to help academic and industrial users. So really serve as a baseline to allow for, again, academia to start building on something that can be improved upon, right? And then you have this constant cycle of usage and contribution. And David Patterson, who is actually the developer of the RISC processor, and he collaborated with Chris. And after a series of iterations, they arrived at the 5th generation of the RISC ISA, and that's how we have the term RISC-V. So even though it's a V, like you pronounce it RISC-V. And then in 2015, the RISC-V Foundation formed. So this was really to appease commercial users, right? So because there was no real person that owned or had some responsibility for the ISA, this foundation was formed to basically have some governance to the ISA itself, to provide some direction, to provide some degree of management to where the direction of the ISA would be headed, and just provide some stability, right? So in the commercial space, that's important. But the license to still use the ISA is still open source. And anybody can go ahead and download it, install it on an FPGA development board, and just run it, make improvements to it, etc. The only thing that's restricted is that only members of the RISC-V Foundation have voting rights to actually enact change. And then in 2020, the RISC-V Foundation was renamed to RISC-V International. Okay, so that's just some history. So now it's the more interesting portion is how can we get involved, right? How can anybody get involved? So this is specifically geared, this particular session is geared to the East Coast in the United States, so New York City specifically. So, most of the activity, especially in the US, is dominated for RISC-V in the West Coast, right? Because obviously RISC-V started in University of California, Berkeley. So, they have a pretty good head start. So what we want to try to do is, bring in more activity onto the East Coast, have more conferences like this one, some webinars, some general talks, just to have a community going in New York City that we can share what sorts of cool projects we're working on, some latest innovation in RISC-V that's happening, and features in academia, in research that's occurring that could enable some really cool features that could enhance just any sort of vertical or domain in general. Okay, so one way that you can get right in on the technical side, or one way to get involved, is just dive right in on the technical side, right? So yeah, and then we'll post slides to the link as well. We'll post link to the slides as well. We'll publish the recording and the slides hopefully as well. So to get involved, right, you can dive right in on the technical side. It just really, it's pretty straightforward nowadays. It's not that difficult to just do like a simple hello world application, like a system level application with RISC-V. You can get an FPGA board, integrate the RISC-V ISA with just a baseline design. There's many repositories on GitHub that demonstrate how to do that. Lots of hits on Google that can show you how to get started. And then you can just write a simple hello world software application with the RISC-V GCC toolchain, and that's all you really need. right? So specifically, if you're interested, that's one way to get involved, right? If you on social media, reach out to Megan or myself, and just reach out to us and say, hey, I want to develop this cool thing. I want to showcase it in potential RISC-V community event. We'll be more than welcome and more than happy to host an event where you can kind of demo your cool projects, your some new feature that you've developed, some hardware acceleration that you were able to get started with RISC-V. Somebody has a question that says any resources on where to get the board. So and really any FPGA board that's sufficiently sized, I think, should be more than capable of handling the RISC-V ISA. I think Tim, when he gives his talk, he might be a more appropriate person. And Tim, feel free to chime in if you have any recommendations right now about what sorts of boards that might be good candidates for like somebody to get started with RISC-V.
I will have some recommendations. Our Digilent RD is very popular. 1-Bit Squared is a company that makes a board called Icebreaker that has a quite tiny FPGA, but you can still easily build many different types of RISC-V cores on that. And I'll talk a lot more about that during my segment.
Sure. So yeah, we'll wait for Tim get more details about that. So getting involved beyond just the technical side, finding venues, finding potential speakers, even just identifying interesting projects, gathering demos, making sure that just doing all the non-technical stuff is actually pretty important, and it is not trivial. It's in its own right. So any help that you can provide would be great for me. It would be a load off of my back substantially, right? And I would be infinitely grateful to you if you want to get involved. So that's just a few ways that we can get involved in RISC-V, both on a technical side and also just arranging events like this one. Like I said, they're not trivial, and it takes a lot into organizing such an event. So anybody that wishes to get involved, if you can feel free to reach out to me or Megan, like I said, right? This is my email address. You're more than welcome to email me at this address if you want to get involved, or even if you have any sorts of questions on RISC-V, feel free to shoot me an email. One person, I think Sergey, who's on the call or who's on the conference on this talk, asked about like setting up a RISC-V community group in a region that doesn't have us, so that doesn't have one. I think that's definitely possible. You can shoot me an email and I can forward you to the appropriate person on how to get that going. So next steps, specifically in New York City, we're looking to have potentially an in-person or a hybrid event in the fall of 2000, in the upcoming fall, so in 2022. Venue, we could have it in a multitude of universities and colleges throughout New York City. We're still open to gather some speakers. It would be nice to have somebody do a potential demo to showcase like how to just get started up and running on RISC-V. So, if anybody has any thoughts, anything that they're willing to help with, again, more than welcome to just reach out to me and be tremendously grateful to you. So yeah, thank you for joining the session. And with that, if nobody else has any questions, we'll kind of send it over to Tim. So let me just introduce actually Tim first.
I thought Kem was going first, but I'm happy to go. I'm ready.
Sure. I kind of rearranged it a little bit just because Kem wasn't able to make it. So he's just sent me a recording. So you're welcome to kind of go if you want to.
Great. And my talk does follow on to Mohammed's comments quite perfectly, even though we didn't synchronize. So let me share my slides. Might take me a little bit here. What does that look?
Yep, we can see CFU Playground, full screen.
All right. Okay, great. To get the acronym out of the way right away, CFU stands for Custom Function Unit. That's the little bit of extra special stuff that you will add to your RISC-V CPU to make it faster or more efficient. I'm Tim Callahan, but this is the work of many at Google and outside Google as well. But it is not an official Google project. It is open source, so you can help. We are very happy to get contributors. And these slides are online at this. And don't worry, if you can't write this down right now, I will have it in the bottom right corner of slides throughout the talk. And I will have a lot of links, so it will be useful for you to bring up the slides for now, or actually even better for after my talk, to go check out a lot of the stuff I have. Okay, so this was a collaboration between the Chromos hardware team, Alan, David, and Dan in Sydney, Australia. My boss, Tim Azel, whose original idea this was to bring this all together. Interns helped along the way, Rachel and Joey. We collaborated with the Tensorflow Lite for microcontrollers team, Pete Warden. And Amp Micro is our contractors we work with a lot, and they've contributed quite a bit. And we also have an ongoing collaboration with Harvard. Professor Reddy Shvetank is actually an intern for me this summer, and Colby helped a lot. And of course, I'll talk more about this later, but we rely heavily on open source. So we're basically just bundling a bunch of different open source stuff together, adding a little glue, and hopefully making it easy and fun to use. So the key ideas is we're focusing on the domain of TinyML. And the idea is that because we're going to make everything soft so that you can specialize your complete stack for just the machine learning model that you're doing. So we're not going to specialize just the software, but the processor itself, just for that model. Because we're developing on an FPGA board on your desk, it's going to be a very iterative, but with fast iterations development process where you're modifying both the software and the processor, enabling you to try a bunch of different things, maybe throw out 9/10 of them, but you'll hopefully find the good idea and then continue from that point and keep making progress. And we also want to make it very low or no barrier to entry, so that, Google, we can fab our own chips. We can make big chips, we can make little chips, but it takes, we have dozens and hundreds of engineers to work on it. We want to make this easy and put it in the hands of small companies and even hobbyists to really unlock the innovation. And RISC-V is just one of the things that enables this. Okay, so if you're familiar with let's say an Arduino board, you plug it into your laptop through a cable, that's how you program it and communicate with it. It's kind of the same thing. We're going to have a USB port that you will program the firmware onto the board and then communicate with it. But the other thing is we don't have a hard processor. We have an FPGA. So the USB is also going to be used for downloading a configuration bit stream, which is what gives the FPGA its personality. It basically is software-defined hardware. By downloading these bits, you can make it into any circuit that fits into the available resources. So this is just a hopefully this will help if you're not at all familiar with an FPGA. There are configurable logic blocks that can be programmed to do any function of 4 or 5 or 6 inputs, and then programmable interconnect that connect them together. So by programming both the blocks and the interconnect, you can make any digital circuit. Now, these aren't very efficient at implementing memory or multipliers. So usually a modern FPGA will have specialized hard blocks for multipliers, memories, high-speed IOs, stuff like that. Okay, so what are we going to do? We have this basically a clean sheet of paper. We can put anything on it that we want. Well, we need a CPU, and it naturally is a RISC-V CPU. We need some local memory. It can actually be off chip, but again, most FPGAs have a local RAM, so we're at least going to use it as a cache, if not for the main memory. We need to connect to the host computer, and we need a system bus to hook it all together. And we need some software. Again, we're focusing on the area of machine learning, but most of what I'm talking about could be applied to any domain. So at this point, we have a complete system. We can run inferences, but it won't be as fast as an equivalent hard processor. So the fun part, and where we're going to really try to exploit the flexibility of an FPGA, is adding a custom function unit that will add maybe just 1 or 2 new instructions, or it might eventually become a complete coprocessor. We'll talk more about that later. But the important thing about this is you only have to worry about the custom function unit. We take care of all the other stuff, and especially the complicated board of mapping this system to whatever FPGA board you have. Now, we don't support every single FPGA board, but we do support a lot of them. And mostly you don't have to do anything to move your design from one FPGA board to a different one, even with FPGAs from different vendors. Now, these are just some of the ones that we've actually tested, and we can confirm that CFU Playground works on them. Even that tiny thing up in the upper left corner is FOMU, and that has an ICE40 FPGA on it, and it really is that small. It completely fits into a USB slot. I mean, it makes things a little challenging, a little fun to squeeze everything in there, and that was an intern project that I hosted last summer. And we'll come back to that, time allowing. But the soundbite here is every FPGA board is a RISC-V development board. Now, you might wonder, how can you support different boards? I mean, do I have to get the schematic of the board and figure out which pins connect to LEDs to use them, and which pins connect to the UART to figure out how to talk to the host computer? And the answer is no. We use an open source project called Litex that has a board library that contains all this information. And now, the bit I'm going to talk about now is not directly related to the custom function unit. It's the underlying open source FPGA and RISC-V infrastructure that we utilize. So these are all the FPGA boards that Litex supports. I know it's a little small, but that's kind of the point, to show you how many different ones there are. And it also supports many different CPUs. And all of the ones in orange are RISC-V CPUs. And I think, I can't see it so well, but I did highlight the ones that are 64-bit CPUs. So you can see that RISC-V has played a role in this open source FPGA kind of explosion of different projects and community. And I mean, behind every single one of these CPUs, there is a team or one person, and they all have their own strengths and weaknesses. For example, SERV, S-E-R-V, is a bit serial implementation of a RISC-V processor. So it is I think by far the smallest of any of these. And I mean, it's continually growing. This one was added just today. Seriously, it was just checked in this morning after a little bit of back and forth on GitHub between the maintainer of the repository and the person who developed this. And they cleaned it up and it looks good and it's checked in and you can, and it is also a new RISC-V implementation. But in CFU Playground, we use VexRISC. VexRISC has been around a long time. It won a competition that Google put on for the fastest open source soft core. And also, we've collaborated with the maintainer of VexRISC to add the custom function unit interface that we connect to. Okay, I could easily spend half an hour just talking about all the existing RISC-V plus FPGA plus open source community. It's a very active community. There's a lot of fun projects. We have run Linux on this board. The board actually is misleading. The FPGA itself is rather small and only has 5,000 LUTs, but yet we were able to boot Linux. I mean, not we, someone in the community booted Linux on that FPGA board. You can put multi-processor, multi-core Linux systems on an FPGA. Olaf's has this very tiny core, and he enjoys keeping score of how many of these he can squeeze on every FPGA that's released. And the current record is 10,000 RISC cores on the latest and greatest Xilinx chip. The VexRISC maintainer recently released a beefier out-of-order RISC-V implementation. And toward the bottom, these are some that I did. It's like, oh, well, there's a new CPU. And oh, I have this board. Why don't I try putting that new CPU on this board? And so that's what I did in these 2 tweets. And I added this just listening to Mohammed speak about the Hello World project. So if you start with the Litex SoC infrastructure, they also have this is kind of their Hello World. It's a little bare metal demo that it brings up a little menu. So it interacts through UART. And so just a little terminal interface, but it has a demo, an ASCII rendering of a spinning donut. I'm afraid if I try to click on it that I'll lose my presentation. So I'll let you click on that. Oh, and finally, of course, we can run Doom. Even on tiny FOMU, we have run Doom on a RISC-V processor. So again, open source showcase. TensorFlow, of course, is open source. RISC-V, we chose because it's open and also because it has many very good documented, high-performing open source RTL implementations. And we chose VexRISC. Again, Litex is the SoC and OpenIP. That's an important part of it too. And we, in fact, also try to use open source FPGA tools. Really, the only proprietary thing in the whole stack is the FPGA itself. And of course, there are researchers looking at publishing open source embedded FPGA fabrics that then will let you have well, in fact, some have already been taped out on the Skywater 130 PDK. And I'll hopefully have time to talk about that. There's just so much stuff here. This repeats some of what Mohammed went over. The benefits of having an open ISA plus all the other stuff being open is the no licensing fees. But probably even more important to Google is you don't have the headaches of having to set up license servers for your build system, which in Google is, our internal cloud. We, in fact, if we use commercial tools, we have to put them over on a different cloud, which is a real pain. So we try to use open source as much as we can. And we do occasionally run into bugs, just like you do with proprietary tools, but we can usually contact the maintainers or submit a fix ourselves and get it resolved within a couple of days or a week. Whereas with commercial tools, you're waiting probably 6 months for the next release. There really is no vendor lock-in. And even more specifically with FPGAs, if you're using the proprietary tools for FPGAs, you use that vendor's CPU. So then you're writing code for that CPU. If you write any assembly, it's for that instruction set. You're using their hard IP, their tools. So now it's quite difficult to switch to a different vendor. Then you have to rewrite your design to use their hard IP, their soft CPU, maybe even rewrite your software to use that CPU, which is not completely unintentional on their part. They like locking you in. Whereas since we're using RISC-V and just the stock GCC RISC-V toolchain, we actually just by changing one command line option, we can go from a Xilinx board to a Lattice board, extremely easily. In fact, we usually do that intentionally. We develop on the RD board here because it's a bit larger and we don't need to worry about resource constraints at first. But then eventually we switch to the target board, which is much more constrained. And there's no pain at all switching from one to the other. Also, if you're very security concerned, you will appreciate the transparency of having an open source implementation of your CPU. You know exactly what's in there. You know there's no hidden RTL. So what is this CFU playground good for? Well, you can deploy a soft RISC-V CPU plus your special Accelerator edition on an FPGA. So you can actually go to market with an FPGA. And this is not just hypothetical. We are actually doing this. We're shipping an FPGA in Chromebooks. There will be a RISC-V running on that FPGA. But if you're doing enough volume and you need to shrink it, then it might make sense to harden that implementation, go to an ASIC implementation. So you could use this as a prototype step going to ASIC. And in fact, our group is also working on opening up the ASIC flow. This link has a good video by my manager, Tim Ansel. And in case you didn't know about this, if you submit an open source design, Google will fab your chips for you at no cost to you. Even if you're not building a product or anything, just fooling around with this is a great way to learn about ML software, hardware, performance tuning. And if you happen to be an ML researcher, this is great if you envision a new algorithm that doesn't happen to map well to the existing hardware, whether it's microcontrollers or GPUs. You can build your own hardware to match the algorithm that you have in mind. Okay, again, this is actually going to ship in Chromebooks. We have a human presence sensor that lives up in the edge in the bezel of the Chromebook, where I marked a little bit of red up there. So it's very size constrained and power constrained because it's always on. So it's going off battery power. So it's really tiny ML. And with something like this, we're very sensitive to security and privacy. So we definitely cannot bring a proprietary binary blob and put it in our build system to build the FPGA tools. So if we are going to use an FPGA here, which we did, the build tools also had to be open source. The FPGA has 48 multipliers, even though it's very tiny. It's about the size of a normal microcontroller. And we use all these multipliers. So it's like, oh, wow, that's pretty high performance. But that's not really why we chose it. It's because of the openness and because we can integrate it with open source tools within our build system. Oh, so anyway, yeah, these are the, I'm not sure if I can say this is the first RISC-V processor in a Chromebook. I mean, even though it's a soft RISC-V, it is a RISC-V. But we're quite sure it is the first FPGA in Chromebook. Okay, so this is probably going to be a review, so I'll go over it and I guess Mohammed went over this. So you choose the RISC-V is open and configurable. You choose one of the bases, then you can add one of the many extensions depending on what functionality you need. And if you've been involved in designing one of these extensions, I mean, it's an open process. It is public, it's open source. So anyone who wants to be involved can be involved as long as you're a member of RISC-V International. So there's many stakeholders with competing priorities and constraints. So there's a lot of compromise. It's a long ratification process. But once it's ratified, the extension lives indefinitely. It can go through some revision with versioning, but basically you really want to get it right the first time. So it's kind of a high pressure situation. The stakes are high. But what I'm going to talk about is kind of the complete opposite of that. It's a custom extension. It's something where you're doing it just for yourself. You don't have to make anyone else happy. If tomorrow you look at what you did today and you decide it's junk, you can just throw it out. You can change it. So these really throwaway ISAs. And it's not like we're kind of breaking the rules of RISC-V by doing this. RISC-V has reserved part of its opcode space specifically for these custom instruction extensions that it's not going to say anything about. It's like, this is your free space, do whatever you want to with it. So I'll give a really quick example here. First of all, let's understand how a regular RISC-V instruction works. Here's a very simple add instruction. We have how it looks in assembly with a nice little comment in case you don't remember which one is the destination. But of course, the processor only understands the binary encoding. So we start by looking at the bottom 7 bits, the opcode, and this says, oh, it's an ALU instruction, and that's a R format instruction, which means it's going to use 2 registers. And well, here, let's look at it with a little bit of the RISC-V data path. So once we interpret the fields, we see that there's the source 1 and source 2 specifiers, and they tell us which registers we're going to get our operands out of. So in this specific case, we pull operands out of register 4 and register 7 and send them to the ALU. Then, what does the ALU do with them? Those are determined by the funct7 and funct3 bit fields. And in this case, it tells it you're going to perform a simple addition. And then finally, where does the result go back to? In this case, it goes back to register 4. And that's one complete RISC-V instruction. So when we're going to use our custom function unit, the opcode is, again, in this special custom space, but we're going to interpret the rest of the bits very similarly. So it's also in our format instruction. So in this case, we're the same thing. We pull out sources, operands from register 4 and register 7. But in this time, we send them to the CFU interface. And it's not illustrated here for simplicity, but we also wiggle a bit that says, oh, there's something here for you. We're sending an instruction to you, custom function unit, so do something with it. We send the 10 bits of funct3 and funct7 out to the CFU to tell it what to do with these operands. And when we get the result back, we use the RD, the destination register field, to determine where it gets placed back in the register. Now, everything you do in the CFU is up to you, but the interface is fixed. So let me go in a little more detail about the contract between the CPU and the custom function unit. So You can get up to 2 operands from the register file. It doesn't have to return a result immediately. It can be multiple. It can even be variable cycles. And the CFU there's flow control on both sides. So basically it says when it's done. And if while it's working, it can't accept another instruction, it will also can refuse that at the request side. The CFU cannot itself directly access memory. So any time you need to move data from memory to the custom function unit, it does go through the through the CPU. There's no other way the CFU can affect the CPU. It actually doesn't even have interrupts, cannot cause a branch or anything like that. It can contain state registers or even complete small memory blocks. You can build a finite state machine within your custom function unit. It can really be almost its own little mini processor. And just for terminology, we have one custom function unit, but it contains multiple instructions up to 1024. And all those different instructions can access the same shared state in the custom function unit. Okay, so how do we use it? Do we build a compiler to automatically map to the new instructions? Well, that's a lot of work, and we really want these quick iterations. So no, you're going to be the compiler. You're going to manually insert uses of your instructions into the code. Because you just were looking at the code and you said you design these new instructions to speed up that part of the code, so you know exactly where it's going to be used. So it's great. We don't modify the compiler at all. We just can download the freedom tools, whatever the GCC cross compiler from Sci5 is. And this is what it looks like in your C code. It looks like a function call, but there's no function call overhead. It's just a macro that expands to an assembly instruction. So first of all, we provide the function that we want to say which of the many custom instructions we want, and then the 2 operands, which are just regular C variables. This is just for future reference. Don't try to understand it right now. So here is like a concrete example. We have 2 variables, X and Y, and we want to perform an operation on them. Let's say it's timing distance, and we have built a custom function unit that when you tell it, when you send out these bits, it'll perform a Hamming distance computation. It is for readability. It usually makes sense to do a pound define so that you can actually, in your code, say this is Hamming distance. Again, it looks like a function call, but there's no function call overhead. It is just a macro that expands directly to assembly. So here's an actual case that we ran through the compiler with 2 different custom instructions back to back. So we load a value from memory, feed it through these 2 custom instructions, and write the result back to memory. And when we compile it and then disassemble it, it has been compiled to exactly 4 assembly instructions. There's no register copy overhead, for example. To me, it's pretty much magic how the assembly instruction and GCC can figure it all out. And you see, it's smart enough to say that, well, like we don't use T2 anymore after we use it the following instruction. We don't use T3 anymore after the following instruction. So it realizes that it can just keep reusing the same register, A5, over and over again. There's many different ways of using it. I'll go over just a couple. There is an immediate response, like Hamming distance. You just supply 2 operands, get the result back immediately. If you want to supply more than 2 operands, you can have kind of cooperating different instructions where you have one instruction to load the first 2 operands, and then another instruction that supplies 2 more operands and then performs the computation. Now, this is an idiom that we use a lot. When we were using a stateful custom function unit, we have one instruction that initializes it, like zeroes out an accumulator, and then the main instruction, which shoves in data, and then the custom function unit does some computation and adds it to the accumulator. And then at the end of the loop, we read out the final result in the accumulator. I'm running a little short, so let me go through fast. Let me just talk a little bit about TensorFlow. It is built for embedded controllers. It doesn't have any malloc, so all memory is statically allocated. There's no JIT compiler, nothing fancy like that. It's just a hand-tuned kernel for each different operand, TensorFlow op, like convolution 2D is very common in image processing. So we unpack the model in memory. There's an interpreter that steps through the graph, and for each node, it says, oh, I have registration for this op type, I go to this code. So because the same code handles all the different convolution operators, it has to be able to handle any parameterization, any shape of input tensor. So it's very general. But a lot of times, your model it doesn't use all different types of convolution. It uses like one very specific type, for example, like a 1x1 filter. And when that's the case, you can check, oh, is it this special case? And then branch to a specialized version of that kernel. And because you know that certain parameters are fixed, you can do a lot of hand optimization. Okay, when you download it and run it, this is what it looks like. You go into a project which is in a project directory is where you build your custom function unit and the specialized software that utilizes it. Make prog is the make target to build the bit stream, which it kind of figures out which tool, it assumes that you have the tools installed, although CFU Playground can install the tools for you. Then you make the software and then make load, puts everything on the board, and then you can start interacting with it. This is what it looks like when you're interacting with it. It comes with software that is this menu-driven thing that lets you run sample inferences on the model, do unit tests, also do micro benchmarking where we can figure out why perhaps we're not seeing the performance that we're expecting. And whenever you run the inference model, it is automatically has profiling built in. So if you look over on the right-hand side, you'll see for each layer, it tells you how many thousands of ticks it took, or basically cycles. So each of these is taking a few million cycles. And then we have another script that compiles, that sums it all up. And then you'll say, oh, I'm taking 80% of my time in convolution 2D. That's where I'm going to start looking for optimization and adding a custom function unit. Okay, this is kind of what I just talked about. You build a model, put it on the board, profile it, and maybe break out a specialized version of that kernel, and then start looking for opportunities to add your new instruction. You measure it and repeat. Again, it's meant to be a very iterative process. So in one of the models, we saw that we took, 3/4 of the time in this convolution 2D. So, okay, of course, it's this huge nested loop. So most of the time you expect is in the middle of the innermost loop. So it's basically this multiply accumulate. Let me just ask Mohammed, how should we try to end it right? Should I wrap it up like right now, or
no. I mean, I think I don't think the timing is hard and fast. I mean, I think if you go over by like a couple minutes.
Okay, so here's an example of this kind of starter custom function unit. Now, you might say, oh, well, we actually have 3, in fact, 4 operands. How can you squeeze it into a 2-operand instruction? Well, we're going to utilize state in the custom function unit. Because input offset is loop invariant, we can basically cache it in the CFU and then use it without moving it over every instruction. Same with the accumulator. We're going to have that live in the custom function unit, because it'd actually be quite dumb to keep moving it back and forth between the custom function unit and a CPU register file. So the accumulator just lives in the custom function unit. Then we only have to move in filter val and input val, and you can kind of work through the plus and the multiply and see how they're routed through. and add it into the current accumulator back into the accumulator. Here's the core of the Verilog. Again, I kind of glossed over the important details. There is if statement here, if command valid, which says actually only do this if the CPU tells you that there is an instruction coming your way. Otherwise, just don't do anything. And here we are back in software after we've done the software replacement to use our new instruction. So again, outside of the loop, we move in the loop invariant value. We just do that once. It turns out the way the loop structure is, we compute a new value in this inner set of loops. So we have to re-zero the accumulator once at this point every time. And then at the innermost loop, we're just shoving the data into the custom function unit. And then once we have a new output value, we pull it out of the custom function unit. And this alone, which is pretty straightforward and simple, gave us about a 1/3 speed up on this TensorFlow operation and a 1/4 speed up overall. But again, that's just the first step. Okay. So this is what we started with. Of course, it makes sense because we're actually working with 8-bit values rather than moving 8-bit value over at a time to do but we have a 32-bit path to memory to pull 32 bits from memory at a time, send it as a unit to the custom function unit, let the custom function unit unpack it, do the multiply, accumulate in parallel. I mean, this is the stuff FPGAs are perfect at. So right there, we get a 4x speed up. Then we start moving some of the data in there so we can get local reuse of the data. And we keep going and going and going. This is what our final accelerator looked like. We move input values and filter values in so that we can get lots of reuse. And it actually enables us to get a peak of 16 multiply accumulates per cycle, which is just, there would be no way feasible doing it with a basic RISC instruction set. You would have to use a vector extension, but this is a very customized, just for this specific loop. It is a very fast accelerator for that. So we're using all kinds of tricks, like we're operating on a block at a time. While we're computing that, we're moving in the data for the next block and pulling out the data from the previous block. So we have all this stuff in motion at the same time. So with that accelerator, we go from over 500 million cycles. And this is it's an iterative approach. We keep improving it, measuring, improve it. We get down to 10 million cycles. So this is a 55 time improvement on that particular operator. Of course, you see, we still have other now operators taking up time. So we have more work ahead of us. Unfortunately, I don't have time to talk about FOMU. That was a really fun project. And please go ahead and take a look at our slides. But it also got a 75 times speed up, not just from custom function unit, but by measuring all types of latencies in our system, which was enabled by developing directly on the board and measuring all things that, versus trying to do this in a simulator. Anyway, we have had great collaboration with open source. Google chipped in a little to get enhancements made in the open source tools that we use, and then everyone can use it. So Google benefits, the community benefits, the people who did the work benefit. Same with Renode. And glad I did get to this slide. The question, in the beginning, I said, this is like when you're building extension just for yourself. But what about when you finally build something that's so great you want to share it? Or you want to build a system that uses the great custom function units that other people made? How can you plug them all together and make sure they don't interfere with each other? So that's what this project, Composable Custom Extensions, is all about. It's work I've been doing with some quite a few engineers here, please click on the link and see how we propose that you can have all these custom function units working without stepping on each other and having it so it just works. Oh, and of course, please check it out. Come join us. And even if you have simple, even if you don't want to get into doing your own extension, you just want to play around with RISC-V on FPGAs using the Litex SoC environment, please send me an email. I'll at least put you in touch. There's a lot of forums and discussion boards where you can get help. Thank you. We can open it for questions now, unless Mohammed wants to wait till the end.
No, if anybody has any questions, they can, I think they should be able to unmute themselves and talk. Or you can just ask a question in the Q&A tab. A minute or so, and then if there are no questions, we can move on to the next session.
So you did ask about FPGA boards. We like Icebreaker, although it has supply chain issues. Although I did get an email recently, so they might be in stock at the 1-Bit Squared store. I don't have a link for that in my slides because I don't want to get into too much obvious promotion, but this is nice because even the board design itself is open source. But RD is always a favorite. You might already have one of these sitting around, although it's gotten a little more expensive than when I bought this one. Orange Crab is nice. It's actually quite high performance, even though it's one of the smallest. It is probably the highest performance of all my FPGA boards. But anyway, next time we have an in-person meetup, I can hand out a few FOMOs. So
awesome.
We love getting people involved.
Yeah, maybe we can have you in the fall, Tim. That'd be great. In person with some FPGA boards.
I would love. I didn't mention I was just in New York City 2 weeks ago, maybe 3 weeks ago now, on Roosevelt Island for a conference called FCCM. That for 25 years it's been about doing computation on FPGAs. So that was a ton of fun.
Cool, excellent. All right, thank you so much, Tim. Next session we have is with Hemraj. He's a fellow at Comcast, and just pull up his bio. So Hemraj is a fellow at Comcast, helping several open source initiatives within the company. He's guiding the company's adoption of open source software and becoming an active contributor to the open source components used in the RDK set-top software stack. One of the most recent projects he has worked on is migrating RDK to an open embedded Yocto project-based framework for build system and embedded Linux distribution generation. He's also actively working on making the RDK community adopt the RDK framework for future TV set-top devices and broadband gateways. He is a Yocto project advisory board member and member of the technical steering committee for the Open Embedded project. He is core maintainer for several key pieces in Open Embedded framework, including core metadata, toolchains, and SDKs. Prior to Comcast, Kem helped Juniper migrate the Junos operating system to use embedded Linux as the base operating system. So let me...
Hey, hello everyone.
All right, so apparently no audio. Let me try that again. Let's see. All right, let's try this one more time. All right, let me try this again. Let's see. So I can hear audio. Okay, so it seems like only browser tab. All right, let me see if I can just open this in a browser tab. All right, let's try this again.
Hey, hello everyone. Welcome to my talk. Today we are going to talk about Yocto. Hey, hello everyone. Welcome to my talk. Today we are going to talk about Yocto project and its application to RISC-V ecosystem. So what are we going to learn today? So we'll know what Yocto project is, and then we'll also know how to get started with the project. And then what's the state of RISC-V support in Yocto project? And then I'll cover some aspects of how you can get involved with the Yocto project ecosystem, specifically if you are interested in RISC-V. And then we'll also see how we can build images using Yocto project, and then we'll also showcase some of this, how they are run, and customizing them, because in the end you want to add your own customizations, maybe new packages, so it's important to know that. And we'll also show how we could use additional components or maybe alternative components if you need to use those. So we'll showcase how you could use Clang as a system compiler. And then SDKs are important when you want to share with someone else. And there are various ways to generate SDKs that are very powerful using the project. So we'll go over that. So that's roughly our agenda today. So let's dive in. So what's the Yocto project? So it's not an embedded Linux distribution in traditional sense. So you might have heard of Fedora, Debian, Ubuntu, and other Linux distributions. The Yocto project is not a traditional Linux distribution. In fact, it's an infrastructure that creates a custom distribution for you. So it's a stark difference that is as compared to other distributions out there that needs to be understood. So what does it provide? It provides you certain tools, and we'll go over that, and some techniques and the ways to do things, which will help you to create an operating system for your embedded Linux systems. It deploys open embedded build technology. Open embedded is another open source project. So all the build system that is used in Yocto project is based off of open embedded build system. There is another tool, part of the build system, is called BitBake, and it's basically the main task execution engine for the build. And BitBake and Open Embedded are actually combined together to create a reference distribution, which is called Pocky. And that's the one that will be also, all the examples you'll see in this talk are actually coming out of the Pocky distribution. So this is roughly what it looks like. As I discussed earlier, Yocto project is actually an umbrella project. It basically have certain open source tools and some of the components that are essential for embedded Linux development, which are maintained there. And they are kind of like provided on this umbrella. And it makes sure that they are kept in good shape so they can be used in various capacities. Pocky is the distribution, as I mentioned earlier, which basically ties it together and presents you as a reference where you can get a starting point and then you can start to adapt it to your needs. So a high-level view of the system looks something like this. So here, as it is putting together an operating system and distribution for you, there are several components that go in. And so there are user configurations, right? So you want to say, I want to use OpenSSH instead of .bear. Or there are other things where you have a specific machine configurations where you might have your BSP, a specific machine that you're targeting. And then there is some policy where you may say, hey, I don't want to allow a certain component to be included, or I want to pin to a certain version of kernel. And I want to use VLAN and not X11. So all those goes into policy configurations. And then you have the source material that comes in. So, the tarballs of the upstream repositories, or maybe, they are directly fetched from GitHub or somewhere using the Git protocol or other SCMs. In fact, Yocto supports different kinds of SCMs. And it could also be your local projects that are, as part of your local checkout. And then that gets combined using these tasks. And, so you see here source fetching, and which basically gets, the original sources. And then patch application is where, you apply additional patches. Maybe you need to build something for RISC-V and the patch is required because it's not upstream yet. And you apply those patches. And then, any configurations you need to do, and then compile it. And after you have compiled it, you install it into a staging area. And from where there is the packager piece comes into a picture, which basically then packages are up into, output packages. Like you could choose whether you want to generate, the deb files, like the Debian, archives, RPMs, or you could also use IPK, which is another format that is popular in embedded systems. And then these become sort of your package feeds. And package feed then goes into your image generation. Or if you build SDK, we'll go over that. And it basically resolves all the dependencies and everything and generates a final image. And the same is true for SDK as well. But as you can see, the image builder consumes the same feeds that otherwise you will publish, say, if you were to submit this into upstream. So that's a high-level view of the project. There is a lot of details that go into this and underneath, and we'll touch base on some of those. So one of the powerful aspects of the project is that it has a layered architecture. What does this mean? So this means you don't get a monolith, which means you don't get all the packages and everything together in one go. But you get like a base core build system and core packages like your tool chains or maybe your system C libraries and everything. Essentially, that comes as part of your core layer. But then there are additional packages that may be provided as additional layers that you can lay on top of your project. And this is very useful for also separating out your board support package layers, because many times they have specific kernels, specific bootloaders, and other board supporting packages that they need to do. So they can be a separate layer. So what it does then is, say, if you were to build for RISC-V and didn't want to build for other architectures, you really don't have to include those layers. So you're only including the machine configurations for the specific RISC-V machine that you're interested in. This kind of reduces the maintenance burden that you have to maintain for your own distribution that you will generate out of it. And it also allows you targeted sharing and collaboration, because if you are interested in a particular a layer, then you can collaborate closely with other interested parties who are also interested in the same layer. And it scales horizontally, because you can bring in the layer you wish to include for your products, or you might have a small project which is like an access point or something, and then you might also have a fully blown server which is providing some microservices or something. Everything can be built using Yocto project. The beauty is that you'll have common infrastructure, common know-how. You can apply the same. You can scale it from a very tiny device, so to speak, and then go and scale it up into like really a beefy image, contains pretty much everything that you need. So that's very powerful. And so this is like a rough picture that how the layered structure look like. It is not necessarily in the order of layering, but it gets you an idea of like how it might look like. So I mentioned about the core layer. So open embedded core metadata provides you those core pieces, like your base build system and your tool chains and core system libraries. And nowadays we have different tools that are in core. You have CC++ compiler, you have Rust compiler, you have Go compiler, Perl, Python, you name it. There are many ecosystems like language runtimes that are available in core, but not all of them are available. So if you were to use Java, for example, then you will have to include MetaJava for getting the Java compilers and Java runtime and other things. Similarly for Mono or others. So those are separated out into separate layers. The idea being that what are the most common pieces you need? They are kind of put into the core layer, and it is purposefully kept to be light. And then you have other hardware-specific BSP layers, like if you're using x86, there is Meta Intel, Meta AMD. If you're using ARM, there is Meta ARM. Similarly, there are other specific BSP layers, not only architecture layers, but there may be like NXP has their own layer, and others, so on and so forth. And then there may be some independent software layers, so UI specific layers. So Qt 5, for example, has its own layer. Qt 6 has its own layer, and then there are like some commercial layers as well. So if you are working in a commercial capacity, you might have your own set of packages that you want to include or things like that. And similarly, you can imagine there are multiple that you can basically put together. So that's what we meant by layered architecture. So getting started. So one of the strong points of the project is it has very good documentation. So essentially, if you go to an embedded project, it really aids you when you look into the Yocto project docs, and everything is very well documented. So you can start with documentation. There are a lot of quick start guides, but then there are detailed documentation as well. And I find it handy all in one mega manual. So, you can go to like a single sort of a page and then, read through whatever you want or search through. There's a wiki. Wiki basically serves a lot of purposes. There are a lot of how-tos. There are information about planning. There's information about certain, meetings or other aspects of it. They're all recorded on wiki. And there are various ways actually you can get involved in the community. So there is a given page I've linked here to get engaged. Mailing list is one of the primary ways that the community interacts, especially when it comes to sending patches or discussing designs or things of that order. However, we do have IRC as well. So there is a IRC server. You can join that IRC server. I think we are on Libera. So and you can join the Yocto room there. We also have open embedded rooms. So same folks hang around in both places and many times. But yeah, so you can join either of them. And there's a matrix presence as well nowadays. So if you're on matrix, you can join the matrix room. It is bridged to IRC, so you have a large presence there for all the developers and users. It's a good place to learn about things and also interact with developers and users online. So I highly encourage you to join these communities. And there are you can ask questions on the Yocto project mailing lists, and then if you start sending patches, we use mailing lists to exchange patches and review them. There are different mailing lists for sending patches for different layers. Obviously, some layers share them, but all that information you will find in the readmes of the layers that you might be modifying. So all that information is clearly spelled out. So before we dive in, so I consider this that using Yocto project is actually like driving a Ferrari, because it is very customizable. You can customize it to the last bit, but then you need to know the controls, because all these knobs are important that you understand them, and you can kind of tweak them to your needs. However, what Yocto project does is it provides you defaults, sane defaults, to get started. So you really don't end up, using something that's very bloated, or something that's very subpar. So it has created this well-oiled reference images, reference distribution, reference policies. That is a good starting point. From there on, it's up to you how much you want to configure it. So there are various things you could do with it. Speaking of RISC-V support in Yocto project, currently it's fully supported in open embedded sense. So we have base 2 machines that are QEMU based, so QEMU RISC-V 64 and 32. So both are basically emulating, the RV64GC and RV34GC ABIs, but you can choose other ABIs too. So there are other ABIs available as well if you are not using. These are like most common used ABIs, which are cross distro. But if you have a RISC-V based system, which probably have a different ABI set, you're not using double float or something, that's easily customizable in there. And then the hardware VSP wise, there's Meta RISC-V, where we are carrying some of the open boards. So it's Beagle 5, you might have heard of that. Unfortunately discontinued, but the support is there. And then there's a Sci-Fi Freedom U540 that is in there, and then NASE D1 has been added very recently. And And there are more, as we go, perhaps will be added as, the RISC-V community jumps in and starts adding that support. Primarily, we basically have them more community-oriented boards here, more like SBCs that are available as commonly to do like developer-focused work. And then I've listed a few here, but these are not only the ones. There are more perhaps out there that are providing RISC-V machines. So Meta Sci-Fi, for example, I personally use it for the unmatched board. So you can build like all the images for unmatched board and the SD card images using, once you include Meta Sci-Fi. And then there is a Meta Polar Fired sock that basically supports the icicle kit. And as I said, there will be more there. There is a bare metal support as well. So if you are building bare metal applications, you could also build tool chains, bare metal tool chains for 32-bit as well as 64-bit. So this is directory structure. So as you can see, bitbig I talked about, and build is where all the build artifacts live, and contrib contains some scripts to facilitate some of your workflows. Documentation has all the needed documentation that we talked about. And some of the, the maintainers, so you can reach out to various folks for the subsystems that you might be interested in. And then the meta is actually the core layer that contains all the core pieces. Metapaki includes, some of the distribution policies. And skeleton actually provides you a skeleton layer that you can mimic to create your own layers. And there are certain reference BSPs that Yocto project maintains. And RISC-V doesn't have a one of those BSPs because they are kind of supported by project members. And right now there is no member who is supporting RISC-V. So therefore, you have like real boards in there, like BeagleBone and others. And scripts contain, again, some of the workflow tools. So how you get started, you basically clone the repository, and it's actually a Git repository. So you Git clone it, you set up the build environment. There's a top-level build script, which basically sets it up, and you just source it. Once you source it, it will generate some of the configuration files for you. And say if you want to build for QEMU RISC-V 64-bit, so you open actually your conf local.conf and you just add the machine type and set it to QEMU RISC-V 64. And now we are kind of like set. So there are actually several reference images that are available to build. So we'll go over a few of them here. But if you have more questions, reach out to the community and we'll let you know. Or actually, they are also well described in the recipes themselves. So you can go through, look through their description. So core image minimal is really a smallish image, which is basically bare minimum kernel and boots you into a shell. Doesn't have much more than that. So when you are bringing up like a new board, this is the image you are trying because it's your bootloader, it's your kernel, and then libc and busybox, and maybe here and there a couple of other packages, but it boots you into a shell. So very minimal, as said, but your primary target when you're porting new boards. Then there is a core image full CMD line, which is essentially like a a fully blown command line serverish kind of image. One of the aspects it has is that it doesn't use busybox, so it uses like full blown command line utilities from core utils and find utils and other places. And as we know, like some of the workflows might be tuned for that. So this is a reference image for that. Core image Sato, that is actually a X11 Sato based UI image. It's used as a reference for building and testing the metadata. And then there is also a core image Western, which basically is building a Western VLAN based image. And a meta toolchain is actually a meta target to build a toolchain that you can, a cross toolchain basically that you can share with others. It's a self-installer. We'll go over how we do that in the SDK section. And there are a few more tools that listed here. Dev tool, bit-bake layers. We'll actually talk about bit-bake layers a little bit later. But yeah, these are also handy tools when you're working. All right, so now you are ready to build an image. So, I chose the smallest image here, and you can just bit-bake core image minimal in your shell. When you're doing a build for the first time, it might take a bit longer because it has to fetch everything. It has to rebuild everything from the ground up. So based upon how powerful your machine is, your mileage may vary. But as said, initially it might take some time to build. But then thereafter, basically has a very strong concept of shared state. So any subsequent builds you do would do maximum reuse. So, you will be basically doing things much faster. It also creates a stash of downloaded images, downloaded packages. So you don't have to go to internet and download all the time. All right, so once you have the image ready, so you will find the images under temp deploy images folder, and under the name of the machine it was built for. For example, if you build for RISC-V 64-bit QEMU, then it looks something like this. So it contains all your deployable images. In this case, your bootloader, your device tree, maybe some of your early bootloader files, and also then your rootfs, which is basically in different formats. It might create ext4 image, it might be other formats, UBI, you name it. You can choose basically for whatever the file system format that you've selected. All right, so we are covering QEMU here, so I'll continue cover that a little bit here. So you run QEMU is the script we use. It is actually a tool that is to facilitate running QEMU images. By default it runs whatever you built last, but then it has options to run other images, and it can also run a different kernel. You can also tweak parameters to QEMU or to kernel, and you can also choose a different machine if you want to. So during development you might want to use a different kernel. You set kernel equals to and point to that kernel file, and it will be able to boot using that kernel. So we'll just show you how this looks like. So we can just see here. So here, this is my workspace, and I just do run QEMU here, and as you can see, it starts booting. So I've already built the image to save time, as I mentioned. So it boots the QEMU for 64-bit. Right now, this is core image minimal. And as you can see, it's using sys5 in it. And there you go. So yeah, so this is what we have here. Right now, it says that very minimal image, so there is not much there, but you can see there are a few things here that you can use. Okay, so now customization. So you can add a package. So this is like a default that what I showed you, and then you will need to do two things. Like you can go to the layer index as is shown above and see whether you want to add a particular package. And then you might have to add a layer. It may not be in the code layer. If it is in code layer, then you don't have to add the layer because it's already there. And then finally, you add the package to your image. So that's what we'll show. So you can see here, bit-bake layers is the tool we're going to use. So you do show layers, and it shows you what all layers are currently added. And then I use here layer index fetch, which basically I'm adding a layer on top of my project that I have here, and I'm adding meta RISC-V here. But you can basically use it for same way for any layer that you want to add. So, so in this case, I also added Meta OE layer. So Meta OE provides some additional packages, and I'm adding it because I'm adding a package that is in Meta OE layer. So as you can see here, after adding that, I need to modify image install variable. So in the conf.local.conf file, which is your configuration file, you will add the needed package, that you want to modify. So here, core image extra install htop. So I'm trying to add basically htop to my image. So I can show you here if I, see here. So I've added here core image extra htop, and then I'll rebuild the image, right? So I'm rebuilding the image here, and it takes a little while for it to kind of get htop and configure it and build it. As I've built all the prerequisites before, so it's only building htop, but generally it is smart to go and rebuild or build the dependencies that may not be existing, and it'll go and build them too. While it's building the root file image, what we'll do is we will basically run the image and show that now htop has been added to the image. So let's see. Okay, so the image has built, and I can then run it, and let's see. And as you can see, it's the same image, but this time it will be having additionally all the dependencies that you need to run htop. There we go. So now we have added htop to our image. And similarly, idea is that you can add any other packages that you wish to. So you'll kind of follow the same concept, hopefully. So now we'll cover, using, say, if you want to use Clang as a compiler. Clang is quite popular nowadays, so you might want to try it out. So it's not in core, it's actually a separate layer, as I mentioned earlier, on the same line. So you have Meta Clang. You do same by adding this layer. So you basically do bitbake layers, layer index fetch, and Meta Clang. This will make sure it will get the layer as well as add it to your project. And then you will set toolchain equal to Clang in your local.conf. So you are indicating that I want to use Clang as my basic system compiler. And there is another knob there to select whether you want to use runtime also from LLVM, or you want to use libgcc and see runtime from GCC. So both options are available. Default is to use GCC runtime. And then there is another variable called Clang SDK that basically ensures that if you're building SDKs, then Clang also gets included into your SDK images. So it's fairly simple to add it, but I will warn you that building Clang requires some resources. So it might take a while for you to build Clang itself. All right, so SDKs are the way for you to share your applications, your systems with application developers and let them build things out of your project. So there are two ways we can do it. One is that you generate a static traditional cross tool chain that they can use in their make files and things like that. And there is a target for that. So you can generate image specific SDK. So we are building core image minimal. So if you say bitbake -c populate _ SDK, it will basically build an SDK that is corresponding to core image minimal. And then you can share this. This is actually a self-installer. So you can share it with people who can install it on their any Linux computer, and then they can use those cross compilers to build. It's handy for like people doing kernel developments or other bootloader development, basically standalone developments. Even for applications, it is okay. but it is not integrated into Yocto, so that's one of the downsides. So extensible SDK is what you use basically for if you want to provide customizations. So it basically pickles the build environment into a self-installer similar to the application SDK. But then it has another tool called DevTool, which basically is the tool you will use when you work with this ESDK. Underneath it, it is using the BitBake technology to do all the stuff, but it offers you a different interface. I pointed it to actually a reference, which is a cool reference. You will learn it in less than 5 minutes, how to use it. And it can also you can use it to write recipes for your new packages, and you can also customize packages. Say, if somebody gave you this with a certain configuration for BusyBox and you wanted to enable another applet, go for it. You can do that in ESDK. And it will basically rebuild, BusyBox with that change, and everything else will be pre-built. The other aspect of it is that you can also make the SDKs upgradable. So you can set a central kind of a feed server for all the SDK components, and then they are actually automatically, like you do apt upgrade, similar mechanism you can do with the SDK here, where you can then supply all the updates to the downstream developers through that. So it's very powerful actually. And it can be redistributed. So let's say if you are not doing feeds, you can make any customization you want, and then you can regenerate ESDK and send that out to your consumers. So it can be redistributed as many times as you like. All right, so that's all I had. So I hope it was useful to you. So we learned about what Yocto project is, how RISC-V is supported in it, and how to get started with it, how you can engage within the community. And we also learned how to customize it, and then some of the advanced concepts about SDKs. So hope it was useful to you. Feel free to reach out to me. My email is at the beginning on the first slide. And thank you. Have fun.
All right. Thank you, Kem, for this session and presentation. Does anybody have any questions they want to ask in the Q&A? If not, then I thank everybody for participating in today's session. Hopefully this is the first of many sessions, and hopefully we'll have more in-person sessions. So next, we're hoping to have the next meeting in the fall, potentially. We're going to try to make this an in-person session this time with hopefully some demos. Maybe we can get some of Tim's FOMO boards, make it pretty exciting. So keep a lookout for your email. Since you've registered for this session, you should be on the mailing list, and we'll send out updates as we make progress and fill you in on the details of the next session. So again, we hope everybody enjoyed the session. We thank everybody for participating, and hope to see everybody in the next session in the fall, potentially. Thank you, everybody.